I'm Lawrence Newell, coordinator of the radio astronomy group of the BAA. I'm here to talk about what radio astronomy is and to show you some of the hardware at my own observatory. Radio astronomy is about observing stars and galaxies with radio waves rather than with visible light. And so you might expect that the hardware is quite different from optical telescopes. This dish, for instance, is set up to view the hydrogen line emission from the gas clouds in our galaxy. It works at 1.4 gigahertz, which is about 21 centimeters wavelength. With the appropriate receiver, you can detect the Doppler shift on the hydrogen clouds as they move around the galaxy and infer the spiral structure of the arms. This is a transit instrument, so we set the elevation and wait for the galaxy to pass through the beam. If you build two identical aerials, you can make an interferometer. If you have the aerials separated by a long distance, you can simulate a large dish and therefore increase your angular resolution in the same way that having a large optical mirror will improve the resolution. Dishes can be used at much higher frequencies than the hydrogen line. This one, for instance, which is fully steerable, works at about 4 gigahertz. The amplifier unit in here is a cheap satellite television low noise amplifier. This plugs into the module at the front of the focus box in much the same way that you'd have a camera at the focus of an optical telescope. There are other ways of making microwave antenna. For instance, a horn like this can be used to receive 1.4 gigahertz from the hydrogen line. A much larger version of this was used to detect the cosmic microwave radiation. These, although they're very easy to make, can become quite clumsy when they get large, so people tend to use dishes. This kind of aerial, known as a Gurgi Aerial, is more commonly used at lower frequencies. This one's intended for about 2 meters wavelength, which is about 150 megahertz. It will be used to observe the sun, and you usually have an array of several of them. At the other end of the frequency spectrum, we have a very low frequency receiver. This one works at about 20 kilohertz. The idea is to monitor Earth-based beacons whose signal is reflected off the base of the ionosphere from a long distance back to your receiver. The state of the ionosphere is dependent on the state of the solar flux, and therefore you have an indirect method of measuring solar activity with very simple equipment. This, for instance, is a prototype of a receiver made for this purpose by the Radio Astronomy Group. So all of these receivers that we've been talking about come back together to be processed by a computer system. The Radio Astronomy Group have developed some software, which we've called Starbase, which is effectively the eyepiece of all these telescopes. Here, for instance, we see a typical screen showing some of the instruments connected. We can take data from all kinds of different sources, not just local instruments, but also from all over the world. For instance, NASA X-ray satellites or other people's receivers in other Starbase installations.